Welcome to Brain Vision.
So we begin by looking at the distribution of electrons and ions. I've drawn a little picture here. The electrons are the little dots, and I've written their charges above them, the little negative signs, and the ions are the circles with the positive signs, electric charge signs above them. The vertical lines just denote distance with d in between them for distance d. So we're going to get the potential. And what we do is we just say, well, the basic unit of potential is E squared over 4 pi epsilon naught times D. But for now, I just have E squared over 4 pi epsilon naught. Now, what you want to do when you make this calculation is you say, well, the electron interacts with the first ion to its right and is a distance d away. So that's negative 1 over d, and it's a negative sign because it's an attractive interaction. So that little curve there I drew is just shows us that interaction, that's a pairing between that electron and that first positive ion. And that it's good to draw between those two ions because that means we've already taken care of that pairing. We don't have to take care of it again later. So now let's go on to the next pairing. So that first electron with the next charged particle will be from that electron to the next electron. That's positive 1 over 2d because it's a repulsive interaction. And now we go on to the next interaction, and that'll be negative 1 over 3d. So now we're done with all of the interactions between the first electron and all of the other particles in the lattice. Now we go on to the second particle, which is that first positive ion, and we see that we have the positive ion interacting with the second electron. So we draw a little curve or a little arc connecting them, and we have negative 1 over d. So now we look at its second interaction, and that's a distance 2d rather from that first positive ion to the second one. And now we're done with it. So now we draw an arc connecting the second electron with the second positive ion, and that's an interaction of negative 1, a distance d away. And now we're done with all of the interactions, and we have all the terms we need. So now we just need a common denominator. But before we do that, we can actually add a bunch of things together. So we go ahead and we do that. And we factor the d out, and we have all of these fractions, and some of them are whole numbers. We have negative ones that we can combine, and we have two 1/2s in there that we can add together as well. When you do this, you get negative 3 and you have 1. The 1/2s combine to give you 1, and the 3 negative ones combine to give you negative 3, and you also have a negative 1/3. So now you get negative 2. Really, that should be a minus 1/3, but that, let's go ahead and scroll down. That changes, yes, to a negative 1/3, and we get negative 6 minus 1 over 3, and that becomes negative 7/3 times e squared over 4 pi epsilon naught d. And if you recall from electromagnetics, e squared over 4 pi epsilon naught is equal to the Coulomb constant K. Or rather, 1 over 4 pi epsilon naught is equal to the Coulomb constant K. So now we just have a simple expression for our potential. We have negative 7/3 times K e squared over d. So now we move on and look at the kinetic energy of our electrons. And the minimum kinetic energy of 2 electrons can be added, and we have L equal to 3D. So the kinetic energy then is 2h squared over 8ml squared, assuming that they are electrons in a box. And we have 2h squared over 9 times 8 md squared. And finally, that gives us h squared over 36 md squared. So now, if we get the total energy, we're going to need to take its derivative with respect to the separation between the electrons to get a minimum energy needed for the electrons. And this energy, this total energy for the electrons, is a kinetic term and a potential term. So the kinetic energy, once again, is E up here, really EK, we can call it that for kinetic, which was h squared over 36 md squared, and the potential was the negative 7/3 ke squared over d. So when we put those together, we get a total energy of h squared over 36 md squared minus 7 ke squared over 3d. We can take a derivative with respect to lowercase d. And taking this derivative, then we set that derivative equal to 0 to get a minimum. And again, if you plot the total energy, you'll see that this value you get for D would correspond to a minimum. You could just put in certain values for the constants and see that it corresponds to a minimum. And you get the following value once you take the derivative. And let's see, putting in the constants, then we have Planck's constant squared, and the K constant, Coulomb's constant, is 8.99 times 10 to the 9 in SI units. We have the electron mass, 9.11 times 10 to the minus 31, and we have the electric charge squared, which the electric charge is 1.60 times 10 to the minus 19. And once again, going back for comparison, the value we got for D was h squared over 42 k me squared. So we finally get a value for D that is equal to 4.99 times 10 to the minus 11 meters. But you can write this in picometers. A picometer is 1 times 10 to the minus 12 meters. So in converting, you get 49.9 picometers. Now, if we think about interatomic separation, we need to know that the density is rho equals 0.530 grams per cubic centimeter, and the molar mass is 6.94 grams per mole. So we can get our next result purely in terms of thinking about units. So we think about molar mass, we think about grams, and we think about particles per mole. And if we take a ratio of molar mass to density, then we're going to be able to get cubic centimeters per mole, which will ultimately result in cubic meters per mole. And so we end up with 13.09 times 10 to the minus 6 cubic meters per mole. Next, we'll need Avogadro's number, like you would use in chemistry, and this is 6.022 times 10 to the 23rd particles per mole. So in taking the ratio of Avogadro's number with the cubic meters per mole that we just obtained, we'll get the number of particles per cubic meter. And this is 4.6 times 10 to the 28 particles per cubic meter. We can take the inverse of that and get the number of cubic meters per particle, which is 2.174 times 10 to the minus 29. We can further take the cube root of that and get the number of meters per particle, which is 2.79 times 10 to the minus 10 meters per particle, which upon conversion to picometers is 279 picometers. So that is the spacing between particles in picometers. So the lithium interatomic spacing here that we have is 5 5.59 times larger. So we've calculated something 5.59 times larger, but it's within the same order of magnitude.